Hello folks, this is Dr. Young, and in this video we're going to talk about one of the periodic trends that is really important, and that is electronegativity. Now there's a variety of trends that are seen across the periodic table. There's atomic radius or atomic size, electron affinity, ionization energy. But the one that I want to talk to you right now about is electronegativity. Sometimes you may see me abbreviate this as just EN because it's quite the big word. Now, electronegativity is super important because we're going to use it to determine things like bond polarity and the types of compounds that two atoms are going to form, the types of bonds that two atoms are going to form, right? So electronegativity, I'll write this down here, helps with determining the type of bond that forms between two atoms. And what we're going to see in the future videos is that these bonds can be ionic, they can be polar covalent or nonpolar covalent. And how do we tell the difference between them? Well, that is based purely on this idea of electronegativity. Now, what is electronegativity? Basically, it's going to be a scale that tells us how much does an atom want electrons, how much does it like electrons, how hard is it going to pull on electrons. So it's a scale that describes basically how, and I'm going to anthropomorphize these atoms for us because I think it's just helpful for us to think about it, but how much an atom wants an electron. Or another way to say this is how hard is it going to pull on electrons? Does an atom, right, a fluorine versus an oxygen, for example, how hard does an atom pull on electrons? And another way to look at it is a really electronegative atom is more likely going to be negative. A really electropositive atom is more likely to be positive when it's in a compound. So this also kind of points to likelihood of being negative. So I'll also say that it makes you more likely to be negative. And whether that's a full negative charge or a partial negative charge, we'll talk about that more later. Like you're not going to find any cations usually that are really electronegative elements. Similarly, you're not going to find very many anions usually if you have something that's very electropositive on the left-hand side of the periodic table. So let's take a closer look here. So electronegativity, right, like I just said, it kind of measures an atom's attraction to electrons. Here's a really truncated periodic table. But the reason I'm showing you this really truncated one is that I want to emphasize here that the trend tends to be that as you move right, you get more electronegative, and as you move up the periodic table, you get more electronegative. And what we have here is these electronegativity values are actually measured values. You can see lithium's 1.0, beryllium's 1.5, oxygen's 3.4, chlorine's 3.0, etc. These are measured values based on bond polarities. You do a whole bunch of experiments and then these form. Pauling has a big scale. You may find periodic tables. In fact, I'll show you one in a second that has a slightly different value, but they're roughly the same. But if you look at the periodic table, right, you go from 1 to 1.5 to 2 to 2.5 to 3, 3.5, 4. So as you move right, you get more electronegative, which is what this is saying down here. Similarly, as you move up the periodic table, right, we have 2.2, 2.5, 2.8, 3.0, 4.0. As you move up the periodic table, you also get more electronegative. So the overall trend here is that as you move up and to the right, you get more electronegative. So up and to the right are the most electronegative elements. Down bottom left are the least electronegative elements. Right? Down and to the left are things, so if you look at like cesium, rubidium, barium, these suckers don't really care about their electrons. They don't really want to pick up electrons. They're not going to pull on electrons. They don't really want to be negative. These are the things that are going to be positive and are likely to really just give up their electrons very, very easily. Then the opposite is true up here. Fluorine is the most electronegative element. That means it's going to take electrons from any other element that it comes across, which is why fluorine gas is so toxic and flammable and hazardous. but it's just super, super, super electronegative. It really wants electrons. It's going to pull hard on electrons. And if it's ever in a compound, it's going to be negative. And like I said, this is just another periodic table. So here's the full periodic table. The thing to keep in mind with these trends is that they are trends. They're not perfect rules. They are trends. So generally speaking, we can still see, right, that over here on the bottom left, things are not very electronegative, and overall in the upper right, things are more electronegative. Now you'll notice that it gets a little fuzzy here in the transition metal area. That's okay. We don't need to worry about that. We're probably not going to see a lot of these metals becoming important for us anyways. We're not taking an organometallics class or anything like that. But what we want to focus on is that things move up and to the right. While I have this here, though, I do want to point out something sort of odd, which is hydrogen. Hydrogen over here, right, is 2.20. It's way more electronegative than anything else in groups 1 and 2. And if you remember from our previous video, right, we said hydrogen is only in group 1 because it has one valence electron, and if it's ionic, it tends to form a +1 charge. But really, hydrogen is not a metal. It doesn't belong over here on the left-hand side of the periodic table. It belongs on the right-hand side of the periodic table. And so this is a really, really, really important point for us, is that hydrogen, in terms of electronegativity, you want to remember that it belongs smack dab between boron and carbon. You want to think about hydrogen being right there between boron and carbon, right? It's more electronegative than boron, but it's less electronegative than carbon. And in fact, it's really close to carbon, which we'll emphasize more in a little bit in future videos. But when you see these periodic tables, you want to immediately think, yes, I know the trend is up and to the right. And you want to think, okay, well, I know that this is up and to the right, but I also got to remember that hydrogen is between boron and carbon, and then you'll be fine. So I just want to ask you some simple questions here, right? So if you take a look at this, I just want you to be able to look at a periodic table and tell me which one's more electronegative, because that's going to help us determine what types of bonds we see, again, whether they're covalent or ionic, etc. So which is more electronegative? You just got to find these. Here I have a blank periodic table, so I'll draw them in for you. So we've got fluorine here, carbon here. Since fluorine, right, and you want to remember the trend is up and to the right. Since fluorine is to the right of carbon, that means fluorine's more electronegative. Plus, we know that fluorine's the most electronegative, so automatically wins. Now, if I compare magnesium versus carbon, actually, I should pause and let you all take a second. You should pause and take a second, look at your periodic table, and finish these other 4. You just need to find them and ask which one's higher, which one's to the right. Okay, hopefully you took a moment to just try that out, find them on the periodic table. Usually for questions like this, the hardest thing is finding them, and then it's easy enough to tell which one's more electronegative. But so if I look at magnesium versus carbon, right, magnesium's over here. Here I have my friend magnesium. Again, they're in the same row, so I just need to find which one's more to the right, which in this case is carbon. So carbon's more electronegative than that magnesium. If I look at hydrogen versus sodium, remember, this is because I'm talking about electronegativity, I got to remember that my hydrogen really belongs like over here, right? I want to think about my hydrogen as being between boron and carbon here. So hydrogen then is way to the right of sodium. And let me draw in sodium in case you don't happen to know where it is. Sodium's right here. Way to the right of sodium, right? Sodium's in group 1. Hydrogen really kind of belongs over here with the nonmetals. So it's definitely to the right and above where sodium is. So between those two, hydrogen would be more electronegative. If I go to chlorine versus bromine, where are those suckers? Chlorine is right below fluorine, bromine's right below it, iodine's below it. So here they're both in the same row, so it's not like one's more right to the left, but since chlorine is above bromine, that means that chlorine then is going to be the more electronegative of those two because it's higher up. Remember, the trend goes to the right and it goes from bottom to top. And then lastly, silicon and oxygen here. So we've got oxygen right here. Silicon is right here. So I'm comparing silicon versus oxygen. Oxygen is not only higher up, but it's also more to the right. So oxygen definitely would be the more electronegative element between those two. And so while this question is very much like, can you find that on the periodic table? What we're going to use electronegativity for is determining, again, what type of bond are we forming. That's really how we tell. A lot of textbooks just say, it's a nonmetal and a metal makes a ionic compound, and two nonmetals make a ionic compound, but that's a real broad. That's too broad. That's too much of a rule of thumb. Many instances in which that is not true, but electronegativity does in fact tell you what type of bond it is. So study up, watch the next video about what types of bonds are formed. Have a great day.